Alright, let's start our video for Unit 8, Day 1. I do want to apologize for getting this posted a little bit late. There was some difficulty getting it recorded yesterday, so trying again. This should be able to be on YouTube and Canvas to get you guys started on Unit 8, Day 1. Hopefully you're able to watch this before coming to class. So, first thing I want you to do is make sure you title your page Unit 8, Day 1, Simplifying Radicals. Make sure we get this part copied down. The word radical is what we use to describe this square root symbol. Okay, and then whatever is underneath the radical we call the radicand. Okay, so we're going to be talking about simplest radical form here. But first, I would like you to take a look along the right side edge of my paper. I've started by numbering 1 to 20. Okay, all the way down, and I'm going to square each of those numbers to talk about this next topic. So make sure you have that copied down, numbered 1 through 20 on the edge of your page. And then square each one of those. So 1 squared, 2 squared, and we're going to write what they're equal to here in just a second, because I want to start us off talking about something called perfect squares. Okay? A perfect square is defined like this. The result of squaring an integer. So when we take our integers, in this case 1 through 20, and we square them, these are what we get. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256, 289, 324, 361, and 400. These are your first 20 perfect squares, and we can continue on with that list if we ever needed to, but for our purposes today, that's what we need to make sure we understand. So when I get these answers over here, these are my perfect squares. Okay, and so we're going to use that with some of what we work on in our first set of examples. Alright, so I want us to take a look at what we call simplest radical form. And there are two rules that we want to make sure we follow. And I'm going to give you those rules, and then we're going to do examples for them. So first of all, there can be no perfect square factors other than 1. Okay, there can be no perfect square factors of the radicand, meaning the number underneath the square root, other than 1. And so let's look at an example that helps us understand that. So let's say we started with the square root of 28. And you'll notice one thing I never do in this lesson, I am not taking the square root with my calculator and using that button and getting decimal answers. In doing simplest radical form, we are not using that function of the calculator to round an answer. We are finding an answer as simplified as we can get it using these rules. And so what we notice is that number 28, or the number 28, is not one of our perfect squares. It's between 25 and 36. And so it might have factors that are on the list. Remember, factors are things that are multiplied together. And so what we want to do is find the largest perfect square factor of the radicand. Okay, you can make a note to yourself if you want. Okay, so we're going to split root 28 into two radicals multiplied together. And this is using a principle of square roots that says the square root of a times the square root of b equals the square root of a times b under the same radical. All right? And so we want to find the two numbers that multiply to give you 28, where one of them is the largest possible perfect square factor. So if we look at 28, 28 obviously can't be divided by 25, or 16, or 9, but it can be divided by 4. And so the largest perfect square factor of 28 is really the only perfect square factor other than 4, or other than 1. So we're going to write the perfect square factor first, And then 28 divided by 4 would have to be a 7. And so the root 28 equals root 4 times root 7. Or radical 28 equals radical 4 times radical 7. And then we start to simplify this because the square root of 4 can be simplified. Since that is a perfect square, the square root of 4 is 2. So we rewrite this as 2 square root of 7. 7 is a prime number and it has no perfect square factors, so this is simplified as far as we can go. Okay? We've got another rule to follow. There's only two I want to focus on this time. The second rule is that there can be no radicals, no square roots, in the denominator. Remember, that's the bottom of the fraction. Okay, we cannot divide by a radical and leave it that way. So you're going to get several problems where we have to fix that using a process that I'll give you in just a minute. So here's your example. Let's say I gave you 3 over the square root of 5. Remember, this means 3 divided by the square root of 5. Okay? In order to simplify fractions, one thing we can always do is multiply top and bottom by the same thing, because when you multiply the top and bottom of a fraction by the same number, you're really multiplying by something equivalent to 1. And so to get rid of this square root on the bottom, we're going to use this process. Anytime you have a square root on the bottom of a fraction, you can multiply the top and the bottom by that square root. Okay? In this case, I want you to understand that we're multiplying by root 5 over root 5. Because that equals 1. Any number directly over itself in a fraction equals 1. So we're going to multiply 3 by root 5 and root 5 by root 5. On the top, it stays 3 root 5 because we can't simplify anything. And on the bottom, root 5 times root 5 equals 5. Technically, you could say this equals the square root of 25, but that just equals 5. So instead of writing all of this out every time, you can just recognize that root 5 times root 5 is just 5. Now, if we could simplify this by doing 3 divided by 5 or canceling out any other common factors there, we should, but in this case we can't because 3 and 5 have no common factors. So that is your final answer. This process is called rationalizing the denominator. Okay, let's take a look at a few extra examples on the next page. I've got to turn my page. If you've got room, keep writing on the same side. Otherwise, start a new page. All right. These extra examples should get you started and ready for class. We want you to simplify each radical using the rules that we just gave on the previous page. A and B are going to go with Rule 1, and C and D are going to go with Rule 2. But you might also be able to use some of Rule 1 on Part D because of the numbers being larger. Okay, and so when we start off with extra example A, we've got 4 root 20. Remember that means 4 times the square root of 20. And so here's how I want you to think of this. We have this 4 times the square root of 20. We're just going to leave that, and in parentheses, I can add parentheses in. It doesn't really change anything. I'm going to do the square root of 20 by fixing that and making it more simple. Remember, 20, while it's not a perfect square, does have factors that are perfect square. The factor of 20 that's the largest possible perfect square is 4. 20 divided by 4 leaves you with 5. And so to simplify this, I've still got this 4 that kind of just keeps dropping down until it has something else that can be combined. And the square root of 4 is 2, but then we still have root 5. And now we can multiply 4 times 2. 4 times 2 is 8. And so our final answer is 8 square root of 5, or 8 times the square root of 5. Okay? Part B works out in very much the same way. You can think of this as a -1 or just a negative sign. All right? We're going to keep that negative and then rewrite root 50 using its largest perfect square factor. The largest perfect square that we can divide by is 25. 50 divided by 25 is 2. And now, we take the square root of 25, which is 5, but remember we still have a negative, we have to write with it, and then we keep our square root of 2. So negative 5 root 2 is your answer for B. On part C, the problem is that we've got the square root of 2 on the bottom of a fraction. Now, I do want to point something out. The square roots that we're using work like exponents, okay? And actually, square root of 2, just a quick little note on the side, the square root of 2 is actually an exponent. It is 2 to the 1/2 power, okay? So any number that you're taking the square root of, that is a half power. Now, you don't have to remember that for the test, but that does help us realize that I cannot divide 4 by 2 before doing that square root, because if you remember from PEMDAS, exponents, which are also square roots, have to come before division. And so we must fix the exponent part of this, the square root. So we're going to multiply the top and bottom by radical 2 to rationalize the denominator. 4 root 2 is what we have left on top. And the bottom now is just 2. But in this case, we can simplify the 4 over 2 now. We can divide those. 4 divided by 2 is 2, and we keep our radical 2. You notice I got rid of the fraction. If you think of this as canceling out each of these by dividing by 2, it becomes 2 radical 2 over 1, but we don't need to write it as a fraction when the denominator is just 1. We can write it like that. All right, that brings us to our final example. If I've got the square root of 72 over the square root of 2, there's a lot of different things we can do. I'm sorry, I just forgot. This should have an extra number written with it. So if you didn't get this done, I forgot to write this down the right way. This would be square root of 72 over 2 square root of 2. I would have gotten halfway through and noticed I made my mistake, so glad I caught it now. All right, to get rid of the radical in the denominator, which is what we did over here, you do not need to multiply by the entire denominator. All we have to change is the radical 2, so that's all I have to multiply by, is root 2. What I multiply by on top, I also multiply by that on top, or on bottom. Okay, top and bottom have to have the same thing. On the top, we can do root 72 times root 2 underneath the same radical. We can just do 72 times 2. Okay? So that on the top part becomes the square root of 144. 72 times 2 is 144. On the bottom, we still have this 2, and now root 2 times root 2 gives us another 2 to multiply, which is 4. But the square root of 144, you should recognize, is a perfect square. The square root of 144, then, is 12, and we're not done until we actually divide these because they can be simplified. We get 3. All right, so that's just some brief examples to go over how to simplify radicals. We will do some more work in class, but hopefully this has been helpful.